Well, good morning, everyone. Hope you guys are doing well and welcome to today's lecture. I hope you guys have a good weekend and you guys have enough energy for the next 1.5 weeks or 2 weeks, 2 weeks left from the semester. And then you have the exam. Luckily, after that, you are going to have a good resting summer. So let's share the screen here. All right. And again, I'm going to turn off my camera, so we'll focus more on the stuff on the screen. So last time we talked about pitch circle and base circle. And now with the assignment that you did yesterday in quiz 9, you have a good idea now what is the base and what is the pitch. Fundamentally, we said when two gears are in contact, we will find the normal line when they are in contact. So this is what we call it a contact normal. And we'll find point P, which is basically the instant center of these two, let's say, gears at this moment. And then we base our base circle by drawing a circle, which is tangent to this normal. And the pitch, of course, is a circle with its center, it's passed through the pitch point or point P. And remember, all of our calculation is based on a pitch circle, and a pitch circle, we show its radius by R or its diameter by D. So when we talk about the radius or diameter of a gear, we are talking about its pitch circle. And the base, if we need it, but we don't use it for any calculation, the radius we use is, we try to use like this lowercase b, indicating that we are talking about the base circle. All right, and since we are here, if I draw a, let's say, cotangent line between these two pitch circles, which is this line, the angle between the normal line and the cotangent line, which will show it by phi, or some people pronounce it phi, but phi is the Greek correct pronunciation, is what we call it a pressure angle. And then we need to know something about the profile of a gear. So in theory, a gear can have like this shape. Let's say this gear that I have, it can have a straight edge like that. And probably in the past, people who decided to design gears, maybe they had the gears to have like this shape. And then slowly they learn that this shape, it may works, but it does not give us a smooth motion. So for example, they found out that when two gears have these straight edges shape, then probably when they work together, the corner are gonna interfere and there's gonna be conflict. So they remove the corner. And eventually they learn that this profile for a gear should have a certain shape to guarantee a smooth motion. Like this graph here, it has to have a certain characteristics. And those, what we call it a involute profile. But what is an involute profile? So we are looking for a curve that guarantee a smooth motion between two gears, and also guarantee all the stuff that we discussed before, like the pressure angle, the normal line when we draw it. And mathematically, they found that if, look at the picture at the bottom left corner, if you have a graph, like this graph here, let me draw it by red. If this graph is a trace of lines, like these lines, always being perpendicular to this graph and tangent to the base circle. So this line tangent to the, at any point of this graph. At any point, if I draw a line tangent to the base circle and at the same time being normal to this profile. So this has to be normal. So it doesn't matter if it is that line or the other one. Let's say this one. The same characteristics. So at the point of contact, normal to the curve, to the red curve, and tangent to the circle, then it provides the smooth motion that we want. And mathematically, this is what they proved, and they call it an involute curve. Okay. So this involute curve, or maybe I'd better show you, because it's an important thing that you guys know where these curves come from. Let me get to my camera here. Okay. So let's see if I have cylinder fixed to the ground and a piece of string. Let me wound this around this cylinder. So for lack of a better tooling, we'll use just this one. Okay. Oh, and maybe then I attach, let's say, a marker to one end of it. Creating knots is not easy. Just give me a second and bring something else. All right, so let's see what we got. This should be good enough. Okay. Guys are ready? So what I do now, so this cylinder is fixed, and while the string is under tension, I open it up. All right. So this is the involute that we can create. Now for a gear, all we need is a portion of that, not all of it. Like a portion of this one gives me the profile for, let's say, one teeth being at this point. Okay, so now let's close that camera. come back here. So this is then what makes the profile of a teeth for a gear. And keep in mind, as I draw, these graphs can keep like continuing forever, but we just need a portion of it. Like here, we just need maybe this portion. Okay, so that's about Involute. And now some terminologies that we need when we discuss about gears, and you should remember them. So if somebody talk about gears, so you know what they're talking, and it's super easy. So now you know what is pitch circle and you know what is base circle. The outer edge circle, it is called addendum circle, and the inner edge circle, it's called dedendum circle. Okay, and it's easy to remember because it's one is you add something and another one you deduct something from the pitch circle. That's why people call like the distance between the pitch circle and the bottom, they call it a dedendum, and from pitch to outer edge, we will call it addendum, like add something or deduct something. And when we talk a depth of a gear, this is the difference between inner and outer edge. Okay, so a tooth thickness is what you can see on this image. Again, from one side of a teeth to another side on the pitch circle. And do not confuse it with the widths. Widths of the circle in the picture at the bottom is what is go inside the screen, like on the picture at the top. So we have the widths and we have the thickness. Okay, so another important parameter is circular pitch. Circular pitch, again, as you can see, is the distance that shows here on the pitch circle. If you want to calculate that, of course, you need to just calculate pi over d, pi multiplied by d divided by n, which n is the number of teeth. And remember, when we write d, it is the diameter of the pitch circle. So, and on the 3D image below, we'll see the similar things. Another important parameter is this clearance circle. Like when two gears are meshed together, what's the distance between the other gear and the one that we have here? There is like a certain rules. They say usually 10% of the depth you should have clearance. What was the depth? It was here. Whatever it is, if it is 1 centimeter, for example, you should have 1 millimeter clearance between two gears. And we have other parameters like the fillet radius here and other things, which again, all of these, you will see them in your future course when actually you design a gear. So let's summarize. We know what is a pitch circle. One very critical parameters for each gear is pitch. In catalog, when you buy gears, this is a number you will see, pitch. Say, okay, this gear has a pitch of 10, 5, 20. And what is pitch? Number of teeth divided by diameter. And again, do not forget, whenever we talk about radius or diameter, we are talking about the diameter of pitch circle, not base, the pitch. Okay, and circular pitch is this value. We show it by lowercase, and it is pi d divided by n. Let's go back one slide. This is circular pitch. Their name is very similar, so do not confuse them. Circular pitch is a distance, but pitch is just the number of teeth divided by d. Okay, the circular pitch is not that a critical value for us. And a fundamental rule, which again, in your assignment yesterday, you should have seen that two circles, when they work two gears, when they work with each other, they mesh together. That's the terminology we use, two gears being meshed together. They should have the same pitch, all right? So it doesn't matter, let's say if I have two gears, let me say, if I have a small gear here and a very large gear there, that's okay. I can have a very small and very large, assuming that in terms of stress and strength, they can work together. To guarantee that they can work together, let's say if it is gear 2 and it is gear 3, and it has N2 and N3, the number of teeth, then whatever diameter or radius that I selected, the N2 divided by D2 must be equal to N3 divided by D3. Otherwise, they are not going to work together. And it's easy to figure it out why. If you just look at the geometry of a gear and the distance on a pitch circle that each has to travel. Because we know when two gears are in touch with each other, you can assume two pitch circles rolling against each other. And if they are rolling, so they are traveling the same distance on the curve on each side. You can check it later for yourself. So using this then fundamental rule that two gears must have the same pitch, if you recall last day, we showed that omega 2 divided by omega 3 is R3 divided by R2, right? And instead of R, if I write D, and instead of D, if I write N over P using the pitch, and since pitch has to be equal, then we get a very nice formula, which we are going to use it a lot. And it says omega 2 divided by omega 3 is equal to the number of teeth, N3 divided by N2. So we talk about base circle, and you know what is base circle now. And why we need base circle? To create the involute, right? We talk about pressure line. So the cotangent line, right? The cotangent line between the two pitch circles and the normal line, which again, the normal line, you know, that's the one that the two base circle, they are tangent to that line. So the angle between these two, which we show it by phi, it's called pressure angle. And this red line, people call it pressure line or pressure or line of action. Because when two gears are in touch, this is the force, the interaction force between them. Let's call it Fn. So Fn is always on this pressure line. So this pressure angle can be small, can be large, but the common angle is 20 degrees. However, 14 is also common, people use. 25 is common, and you can easily figure out the bigger the pressure angle is. Let's say if you have a tooth this shape, not that just gonna exaggerate a little bit. Let's say a gear like that, or a gear like that. So this is like this one has a large phi, small phi, right? So the larger the phi is, it's the motion between two gears is going to be smoother. So you can imagine climbing up of a, let's say, a slope like the one at the top is easier than the one at the bottom. But the one at the bottom is of course, more efficient. However, it's going to be larger force on the gear and the teeth might break, right? So unless you use a very strong material. So you can use as a practice, let's move this guy over there. So on the picture here, see this is the pressure angle, phi. If I have Fn, I get the component Ft and Fr, and Ft is the one that is doing the rotation, most of the work, right? Fr is just going to the center. So the torque that I can get on a gear will be Ft multiplied by R, which again, R is the radius of the pitch, right? I emphasize it because I've seen students making mistake. So, and you can see Ft is Fn cosine phi. So the smaller this phi, the larger this Ft is going to be, right? So I guess with the knowledge that you have now from MEC 260 or from any other mechanics of material, you should be able to calculate the stresses for a teeth. You can do it as a practice. You don't need it for this course, but just try to see if you can calculate it. If you couldn't, you can always ask me. The way you do it, visualize a gear as more like a cantilever beam. Let me rotate it like that. So it looks like that gear. Okay. So you estimate a gear more like a cantilever beam. So this is the thickness of a thickness, and you have the widths, which is going to your screen, right? And at a point of contact, you have two loads. One is Ft and one is Fr, which you know what is Fr is Fn sine phi. So how you can find Ft? Oops. Ft is easy to find because you apply a torque, you attach your gear to a motor, so you know the torque or you know the power, and you know the relation between power and torque. Power is equal to torque multiplied by omega speed. So you are using a motor, so you know its power. You know how fast you want to run the gear, so you can find torque. If you know torque and you know the radius of your gear, so you can easily find Ft, and you know your pressure angle, so you can find Fr as well. So you estimate your teeth as a cantilever beam, as I showed here. You know the thickness of each teeth, and you know the width. So you treat a teeth more like a cantilever beam, and you should be able to find the stresses. Like there is one sigma coming from FR divided by area, right? And there is another sigma because of bending. So this is normal and this is bending stress. Normal stress, and this is bending stress. And you know how to calculate each of these items, right? Like for example, I, you know, it is 1/12 BH3. If you show it by H, and this is B. Yeah, do it as a practice for yourself. This is one of those critical things. As a manufacturing or mechanical engineer student, you should be able to calculate the stress for a teeth in a gear, but it's not a requirement for our course here. This is something that you should be able, from the knowledge you get from 260 like this simple geometry, you should be able to calculate. So next year, when you learn how to design a gear, like selecting a material and checking if the widths of the teeth are appropriate, then you can check all of these. Otherwise, you're going to design a gearbox which all the teeth are going to break and done. Okay. So, and then number of teeth, there is no like rule saying that each gear should have this number of gears. The more gears that we have, of course, the gear is going to be smoother. It's more like when you are walking, let's say, up a stairs, if the number of, let's say, steps are more, so you're going to have a smoother motion, but it's going to be, of course, slower, maybe less efficient, right? Let's say if your step is small, or let's say if you have like big steps. But as a general rule, again, we know two gears working together, they must mesh, and to mesh, they must have the same pitch. Okay. And we know what is pitch, n divided by the diameter. So that's about it. Internal gears, the only difference, as you can see, the teeth are now inside. And unlike a normal gear, that let's say the teeth, maybe I should use a different color. Like the teeth here, instead of being convex, they are concave. Shape here, they are concave, right? The shape of the involute is concave now. All the parameters are the same, all the definitions are the same, like the pitch circle, they have to mesh, everything is the same. But why people use internal gears? Because manufacturing them is more difficult. The only reason is because they are compact. Like imagine the same gears. Right now, my inner shaft is here and the outer shaft is here. But if I wanted to make the same gear, I have to, like with the outer gears set up instead of internal gears. Like this inside gear has to go out. So I need a bigger distance between the center distance of these two, right? So I took a lot more space. So if we don't have enough space, maybe we need to rely on internal gears. So I'm going to stop here to check if there is any question in the chat. So for the pitch, the unit that you use, people usually they don't use a unit, but if you want to, let's say, select a unit for it, n divided by d is just going to be, let's say, a number divided by 1 over meter, for example. So because number usually doesn't have a unit. So, but I've never seen people use a unit for pitch. They just say, okay, the pitch for this circle, for this, let's say, gear is 0.2. So can we have the internal gears to be helical? Yes, the internal gears as well, they can be helical gears. Remember from last lecture, we said the gears, they can have, I guess it's next slide, right? Yes, somewhere here. Yeah. If you recall, we said the gears can be a spare gear, and a spare gear, the edges are parallel to the shaft, like the edge here is parallel to the shaft. But helical gear, I showed you, there is an angle between them. So if same gear, if I show the top view, where are my lines? Okay, somewhere here. This is one gear, and then the other one. So if this is the shaft for this guy and the shaft for this one, so the teeth, now they are not parallel to, like with respect to the shaft or the main axis, they have an angle. And if one of them is right angle, the other one is left angle. Right angle, like you will see here, the slope is positive, right? And the other one is left. And the internal gears the same, they can be helical as well. And this angle, we call it a helix angle. We show this one by psi, not phi, psi. It's called helix angle. So next time you are buying a gear, so on a catalog, you'll see, okay, this is a helical gear and its helix angle is, for example, 10 degree, 5 degree, usually a small angle. And I showed one helical gear to you. Always, so another question, yes, always there is advantage. Like when you use a helical gear, always there is an advantage compared with a spare gear. Helical gear, as I told you last day, they are smoother, they are stronger, and the reason for being stronger, I want you to think about the area when they are under bending. Let's say for each one teeth that you have, you apply the force, right? And I told you to treat it as a cantilever beam. So if you treat it as a cantilever beam, right? If you treat it as a cantilever beam, imagine like the area going into your screen, and now think about the same things for a helical gear. It's a bigger area. Although these two gears have the same widths, like the one on the top and the one at the bottom, they have the same widths. Like when we say about widths, You guys remember which distance we're talking, right? Talking about, let's say this is the width. I wish people call it thickness, but anyway, width. So widths of these two are the same. Like if you look from like this schematic that I draw here, this is the width. But with a helical gear, the area on the base, when the teeth is attached to this base cylinder, is bigger. So it means it is stronger. And also it creates a smoother motion because these two, as I showed you last day, gradually involve with each other. On Wednesday, I will show you how you can create these gears, like a 3D gears. So if you like to print them, okay, so that's going to be then the plan for Wednesday. If I forget, please remind me. And maybe if you play with that, you're going to get some good ideas, similar to what I showed you last day. So you can see how things are working. And it's going to be good for your future course. But I will show you, and then in summer, you can play with it. So it's super easy, in fact. So please just remind me if I forget. No, I won't use SolidWorks. I will use Fusion, which is like a better tool for that, but they are using the same concept. So, but whatever I'll show you, then you can use SolidWorks as well. And Fusion, Autodesk Fusion is free for a student, so and it's way better than SolidWorks. But I will talk about it on Wednesday and show you how you can make these gears and how you can make files ready for 3D printing. So if you have a 3D printer, you can send it for 3D printing. And then two other types of gears. One is bevel gear, and the picture on the right. In a in-person setup, I usually had like this big box of gears, which I brought to the class so student could see, but unfortunately now, and last day I tried to use my document camera with just some plastic gears, toy gears, but the real one are better, of course. But from these pictures, and of course, you guys can Google them and see them. A bevel gear or conical gear, it's because they have a shape of a cone, like as you can see on this picture here. Right? You can think of a conical gear, two cones rolling on each other. Like there are two cones. So their center like, must intersect, like their axis must intersect. But when we manufacture them, of course, we don't need to manufacture the whole cone. In theory, there are two complete cones, but we cut the extra and we just keep the portion that we need. So the picture on the right is clearly, you can visualize these two cones working with each other. So it's good when we want to transmit motion when two shafts are intersecting. Like here, let's say for some reason, the picture on the right, on the top, let's say our motor, we have to put it vertically, but we need to transfer motion horizontally. So there is no other way. We have to use a bevel or conical gear. And then worm gear, and the picture again on the right bottom, and when we want to transmit motion between two axes, which they are not in one plane. Like here you see, this is the main axis for the worm. This is what we call it, the worm. And the other one is the one that coming out of your screen here, or the schematic on the left, which clearly it shows it. So what's the advantage of this worm gear is when we want to have a super high speed ratio, let's say 1 to 100. You want this guy to rotate 100 revolution, and you want to, like this one, to rotate 1 revolution, let's say per minute. There is no way that you can have this ratio with regular gear. Imagine if you want to have the same ratio with regular gear, then you should probably use a gear with a radius of 1 centimeter and then another one radius of 1 meter, right? It's not possible. Or with conical gear, the same problem. But with the worm gear, that's possible. So the worm, the one at the top, is what people call it a screw as well. It's more like the power screw, similar to what you saw in a very earlier lectures. And keep in mind, this is another mistake that students, they do. The worm gear is just one direction. It means if the worm rotates, the gear rotates. But if your gear rotates, it cannot move the worm. Let's see again if I can get to my camera. So much things going on when teaching online. Lots of things here. Okay, so let's get rid of these involute. Okay, it's here. I have one gear here, and this is, let's say, the worm. They mesh? No. These two mesh, yes. Something like that. All right. So imagine the axis for this one coming out of your screen, and the axis for this guy is here, like this shaft. So if this guy is fixed, if I rotate it, it's more like a screw. It depends if it is the right hand or left hand, it's just going to move, right? It's just going to move over here. But if I have an axis here, instead of this guy moving, if this one is fixed, this one starts rotating. However, if I rotate this one, like the bottom gear, it just want to move left and right, but we don't want this one to move left and right. So the only way for transferring motion is for the worm to rotate and then rotate the gears. Okay. And another things, when I show you on Wednesday, probably you will see it in action as well. So to summarize, 4 types of gears: spare, helical, bevel, and worm gears. There are other type of gears, but they are rare. And these 4 are the one that mainly we will build gearbox using these. So what is a gear train? Gear train is a gearbox. Several gears working together, we will call them gear trains. And all we said so far was just an introduction for this course to get to this point that we are going to analyze 3 types of gear trains: simple, compound, and planetary. So our next lecture and the one after is going to be on these 3, which the slide is coming after that. But what is simple, what is compound, and what is planetary gear? Let me get back to my camera again. Let's move that one. Okay, so I told you before, but one more time, and so you remember them. And then we're just gonna, as of next lecture, focus on the formula. When all the gears are in one plane, we call it a simple gear. So this is simple. So, oh, it doesn't write. Anyway, I use that one. So this is simple. So this is simple. All the gears are in one plane. You start from one shaft, second, and so on. And we said you guys could transfer the motion like that from here to there, but it's going to create a lot of stress on the small one. So that's why we have these middle guys there. And you will see in the formula that the middle one are going to be redundant. They just have the task of reducing the stress on the small one. So from small one, the medium, bigger, and then larger. Now the same scenario, if let's say I transfer the motion like that. Of course, this shaft, they have to be on bearings, as I showed you last day, right? Bearings. Imagine that they are on the bearings, this shaft. So the way it works, the first gear here, transfer motion to these two. These two have a common shaft, okay? They have a common shaft, and then they transfer motion to the other one. So it's something like that. All right, so try to visualize what's going on. So this guy is rotating these two. Okay, so this one is rotating this guy, but they have a common shaft, and as a result, they have the same speed, and then this guy transfer motion to the other one. Why do we use like this combination? Because with a simple gear, we need a lot of space, but if you use this, of course, not the one that I showed here, they can be more compact. For example, I can have this guy over here. And now if you look from the top, I'm using less space rather than having all of them in one plane. So this is then the second setup, which we call it a compound. And the last one, which we are almost done with our lecture today, is a planetary gear, like the best one, which is in fact combination of these two. I wish I print them using a red color. So I just print this one for the lecture today. So how does it work? Planetary gear, something in the middle, which we call it a sun and planet. They are around. It can be only one, but to balance the forces, people usually use 3 or sometimes 4 or 5. But even with one, the system works. And then the outside one, we call it a ring. And this one, which attach all of them, it's called a carrier. Okay, so the carrier. So this is how it works. Let me disassemble it. And as you can see, the one that I printed is a helical. So the gears are helical. They are not a straight edge gears. Okay. So we don't need these two. I have, let's say, the carrier, the sun. So the sun can rotate around carrier. And then I have the other one, and they are helical, right? So if my carrier is fixed, like I don't move my hand, it's fixed, these two gears are like normal, simple gears work together. But if, let's say, if I fix the top one and rotate the carrier can rotate, right? Or if I fix the sun and rotate the carrier, then the planet can rotate. Now, if I use a ring outside, if I rotate the ring, for example, the sun is rotating. If I rotate the sun, the ring is going to rotate. So the whole planetary gear can work with this setup. So how many gears? 1, 2, 3. The sun, the planet, and the ring. And of course, the one that connect these two, which we call it a carrier. Why do we use extra one here? It's just to balance the forces. So in practice, people normally use 2, but 3 is the most common. Using 3. Okay, so enough for today. Let me move back here. And please review this lecture. From like on Wednesday, we will do calculation for each of these 3: simple, compound, and planetary gear. And please do a little bit of Google, maybe on YouTube, and see. I also put a link for you on this lecture, I guess somewhere down, which you can see how planetary gear works. And try to visualize how these things work, because we're going to focus only on the formula, how gear trains can be calculated. Okay. So that's enough, but you guys, if you want to leave, and if you guys have any question, I can stay in a room to answer your question. Okay.
Hi, Professor. I just have a quick question. What is there office hours on Tuesdays typically?
Not on this Tuesday, but if you need any help with anything, just send me an email and I'll set up an office hour. Tomorrow, I don't promise, because it's going to be a very hectic day for me. But definitely next week, we're going to have office hour, and the week after.
Okay, awesome. Thank you so much.
But if there is any question that you guys have, or any help that you want, as I announced at the beginning, just send me an email and I can set up an office hour. 10 minutes, half an hour, depends on how many questions you have. Like the one that is 1 hour is usually I set them up on Tuesday or Thursday, week before exams. So, and solving extra problems. Okay.
Cool. Thank you.
All right, no problems. So see you guys later.